All right, well, hello everybody. Thanks for coming out. So, my name is Ben Prytherch. I'm from the Statistics department here at CSU, and I'm going to talk to you today about what I've titled the case against statistical significance. Before this started, I looked at the roster of people here. I was delighted to see that we've got, looks like people across every college at the university. So this is really cool. Feel free to ask questions as I go if you want, or argue with me about things. There might be some places where we get there will be room for disagreement, and then I'll try to leave plenty of room at the end of this for questions and for discussion. And just so you know, I'm recording this. We're going to put this on YouTube, so once this is up, we have a little Stats Department YouTube page, and I'll send an email to everybody who registered with that link. If you're interested, you can share it with your friends and relive this experience as many times as you want. So welcome. Okay, so the case against statistical significance. I better start with a disclaimer, which is that the opinions I express here are not necessarily those of the CSU Department of Statistics. I'm going to be talking about some things that are controversial. I'm going to talk about some things that are uncontroversial. But statisticians don't agree on everything. We agree on math. So, like if there's a theorem that's been proved, we're all like, cool, we accept that. But there's a lot more to statistics than math. There's a lot of judgment, there's a lot of decisions about how we use things and how we interpret things. And that's where there can be room for disagreement, and the matters I'm talking about today are, I suppose, particularly controversial. But I am going to claim that there is broad consensus on some of these topics. In fact, there's a few of my colleagues in the room today, and they probably aren't going to agree with everything I say. So just get that out of the way. Some of you may have seen this. So this was a piece of commentary in Nature magazine. Scientists rise up against statistical significance. These authors and more than 800 signatories call for an end to hyped claims and the dismissal of possibly crucial effects. I'm proud to say I was one of those signatories. And so what's going on here? Well, you can see in the picture, it's lovely. There's we've got this old book full of papers that are falling out. It's labeled statistical significance. We're going into the closet with air and earth and ether and water and blood and phlegm and yellow bile and black bile, and there's a cyclops skull and all that. So, oh my God, they're telling us we're supposed to consider this outdated. Why? So that's the topic of this talk. So my outline is I'm going to just explain to you what statistical significance is in the first place. Most of you have heard of it, and you probably have different levels of familiarity with it. I'm going to talk about this special issue of the American Statistician journal that came out this year titled Moving to a World Beyond P less than 0.05. I'm going to go through some criticisms of statistical significance itself. I'm going to talk a little bit about p-values and distinguish the p-value issues from the statistical significance issues. They're not the same thing. And then I'm going to go through a bunch of recommendations. Some which were given in the special issue, some which have been given by other people. So, what is statistical significance? Usually this is the thing that we say if we do a hypothesis test and we get a p-value less than 0.05. So you push the button in the software and it spits out a bunch of stuff. Some of those things are p-values, and if the p-values are less than 0.05, there's little stars next to them, or they're color-coded in a special way. So clearly something special is happening. If we get a p-value less than 0.05, we say, go ahead, comment in. We say the results are statistically significant. So the way we compute these things, well, we have this null hypothesis that is set up, and this thing called the null hypothesis, it's different depending on what kind of test you're doing. It's usually along the lines of, there's nothing interesting going on here. The effect that I think I'm trying to estimate is actually zero. All of the variability I observe in my data can be attributed to quote-unquote random chance. I won't take that word too seriously. I don't inject too much meaning into random chance, but that which we model is random chance. At least. Here's the definition of a p-value, which I'm sure those of you who have seen this before just love it. That the probability that, if the null hypothesis were true, a new sample of data from the same population would produce a test statistic at least as large as the one calculated. For something so popular, that feels weird. And if that feels weird to you, that's good. It should feel weird. And there isn't a great way to condense this down to something simpler, unfortunately. And unfortunately, when we do try to condense it down to something simpler, we end up with stuff that's wrong. So here's the reasoning behind this. So if you get a small p-value, what you're saying is the data that you just collected, they don't look like the sort of data that you'd expect to see if this null hypothesis were true. So the null hypothesis, again, is like there's nothing interesting going on. And you say, okay, how likely would it be to get data like mine, we'll say, or more extreme than mine? If, in fact, this null hypothesis were true, if that p-value is small, you're saying, okay, small chance of the thing that just happened happening if the null hypothesis were true, and so therefore I'm going to conclude that my results disagree with the null hypothesis. If the p-value is small enough, I'm going to reject the null hypothesis and declare the results statistically significant, statistically significantly different than whatever's being stated in the null. So some common examples, two-sample t-tests. You have, maybe you've got a control group and a treatment group, and you collect data for both, and you calculate means for both, and you compare the means to each other by this t-test method. Well, the null hypothesis here is that the population means are exactly the same. And so if your data, your means will be different from each other by some amount, but we know they're going to be different from each other by some amount. What we're interested in is, are they different by each other, different from each other by more than we would expect just due to chance if we found the population means were different, meaning that we're the same, meaning that there's nothing going on. And if so, we declare those means statistically significantly different for each other. Or if you're doing regression, you've got a slope coefficient and the null hypothesis that the population slope is 0, meaning like the overall population level relationship between my predictor variable and my response variable, perhaps we're controlling for some other predictors, is precisely 0. And if your data disagree with that by enough, then you reject the null and you declare the results statistically significant. And so here are like some visual examples here. So that top one is maybe two-sample t-tests. I just simulated these data. These aren't real, but they look kind of like real data. Control versus treatment. And so that would be a bunch of data from the control group, that would be a bunch of data from the treatment group, and you can see with your eyes that like the mean for the treatment group is bigger than the mean for the control group. And my p-value of 0.0006 tells me that a difference this large, with this sample size, would be, and that amount of spread, would be really unlikely to occur just by chance. If in fact there were really no true difference between control and treatment, at least in terms of their means at the population level. Down here, this is the regression example. So this is a scatter plot. I've got maybe predictor variable on the horizontal axis and response on the vertical axis. And there's my data, and I draw that line through it, and that line has a non-zero slope, suggesting a positive trend. And the trend is what's strong enough that I don't think I would get data that look like this if in fact there were no population level relationship between these two variables. My p-value is 0.00004. So very, 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 very small chance of getting data that look like this if in fact there's no relationship between these two variables. And so we would say that this is a statistically significant relationship, or more precisely, we'd say that the slope of this line differs significantly from 0. Where this came from, so that's a picture of Ronald Fisher, who created and popularized a lot of the methods that we use today, including the significance test. So Fisher popularized this p-value, and his interpretation of a small p-value, as it says right here, either an exceptionally rare chance has occurred, or the theory of random distribution is not true. The theory of random distribution, he means the null hypothesis, what we would call the null hypothesis. So if you get a small p-value, yeah, it's pretty reasonable. Either this null is not true, or something that doesn't happen very often just happened. As far as his opinion on using p less than 0.05 as a standard evidence, I didn't mention the 0.05 thing, or did I? It's just standard. We have a cutoff. If you're going to make a declaration of statistical significance based on a p-value, you've got to have a cutoff somewhere. Fisher thought 5% sounded pretty good to him, and we're like, well, you made it, so we'll use your number. You don't have to use 0.05, but people might look at you sideways if you use, like, I'm using a threshold of 0.062. And like, why? 0.05. So here is his opinion on the use of 0.05 as a standard of evidence, which may surprise some people. We thereby admit that no isolated experiment, however significant in itself, can suffice for the experimental demonstration of any natural phenomenon. In order to assert that a natural phenomenon is experimentally demonstrable, we need not an isolated record, but a reliable method of procedure. In relation to the test of significance, we may say that a phenomenon is experimentally demonstrable when we know how to conduct an experiment which will rarely fail to give us a statistically significant result. Rarely fail. You're supposed to do it over and over again. According to Fisher, you're supposed to keep getting p less than 0.05. If you keep getting p less than 0.05, then you're supposed to say, we have good evidence for our theory. According to him, you weren't just supposed to just do this once and declare victory and move on to the next thing. Of course, it's easy for a statistician to say that, isn't it? He was working at an agricultural research station where the data were plentiful. You know, he's applying fertilizer to plots of land and comparing crop yields. And you can do this every year. You collect more and more data. But a lot of the terminology we have in statistics refers to plots. He's using literal plots. And then actually at the research station he was at, he had a bunch of historical data to go through. He had decades worth of data that he was hired to analyze. So it's easy for him to talk about doing it over and over and over and over again. For many people, depending on your field, it's much harder in practice to just do the same experiment over and over and over and over again. But in principle, that's how you're supposed to establish strong evidence using statistical significance, at least according to Fisher. So there's a special issue of the American Statistician, which is the flagship journal of the American Statistical Association. This came out this year. It's free and open source and only available on open sessions and open source. It's free and available online to anybody. 43 short articles, and the lead editorial gives this recommendation: don't say statistically significant. So here's the quote from it. We conclude, based on our review of the articles in this special issue and the broader literature, that it is time to stop using the term statistically significant entirely, nor should variants such as significantly different, p less than 0.05, and non-significant survive. Regardless of whether it was ever useful, a declaration of statistical significance has today become meaningless. Statistical significance was never meant to imply scientific importance, and the confusion of the two was decried soon after its widespread use. Yet a full century later, the confusion persists, and so the tool has become the tyrant. Ooh, wow, bold language. I should say here, this is the lead editorial. It was written, there are a few co-authors, one of whom is the executive director of the American Statistical Association. This is not, however, an official American Statistical Association policy statement. They do have an official statement that I'm going to talk about later on p-values. That's a lot less colorfully worded than this. If it's an official statement, it's not going to have language like that. But anyway, there's a lot of people who are kind of on board with this. I'm kind of on board with this, and so I'm going to explain to you why. As far as how this special issue is set up, they got a few different themes. There's a lot of short papers in here. So trying to get to a post p less than 0.05 era, I'm going to explain why we even want to do that in the first place. Interpreting and using the p-value, maybe supplementing or replacing the p-value, adopting a more holistic approach to analyzing and interpreting your data and doing inference. Reforming institutions, that's a big one. I can stand up here and talk about what I think people ought to do all day and nobody's going to listen, so well, hopefully y'all are listening. Changing publication policies, changing statistical education. The lead editorial goes along, and there's a bunch of don'ts. Don't do all these things. So don't base your conclusions solely on whether an association was found to be significant. Don't believe an association exists just because it's significant. This number 3 is a big one. Don't believe an association is absent just because it was not significant. That's a big no-no. I'll talk about that in a minute. Don't misinterpret your p-value. I'll talk about that more later on. And then he says at the end, or they say at the end, don't say statistically significant. So as far as the criticisms go, this is an outline of the criticisms of significance that I'm going to present to you. You can decide how you feel about these. Confusion of significance with meaningfulness, I think, is a problem. I think the opposite's a problem too. Confusion of non-significance with meaninglessness. Publication bias is pretty nasty in many fields, which is the tendency for statistically significant results to get shared with the world and for non-significant results to just sort of go away. Effect size bias is a result of this. The phenomenon of publication bias tends to lead to the results that we see get published being overestimates of whatever the truth is. Unnecessary dichotomization. Well, I'm going to argue it's unnecessary, at least. And I think a lot of this stuff has led to bad incentives. In scientific publishing, so for the first thing here, confusion of significance with meaningfulness. It's kind of an unfortunate term that was chosen for this p-value less than 0.05 thing, significant. Significant means something in ordinary English that is very different from what it means in statistics. If you go look up significant in the dictionary, you're going to see things like noteworthy, important, large, perhaps. And a statistically significant result doesn't need to be noteworthy or important or large. So here are some examples of like borderline statistical significance. So again, I just simulated these, but there's control and treatment. P equals 0.015. If I hadn't drawn those box plots, you might have to squint at that for a second, or relax your eyes and say, which one of those is even bigger than the other one? But this one is, treatment here is statistically significantly larger than control, because its mean is. Again, the scatter plot down here, if I hadn't drawn that positive sloping line through that, would you be able to tell with your eyes that that's a positive correlation? Well, I can tell you it's a statistically significant positive correlation. Now, of course, I intentionally picked values just below 0.05, but they don't have to be just below 0.05. Let's up the sample size. So when sample sizes are large, everything is significant. I shouldn't say everything. Sometimes, I'm actually really, really impressed. When I see a test out with a really huge sample size and they don't get significance, I'm like, wow, that's really impressive. Because look, I've got control versus treatment up here. You can't tell the difference with your eyes. Can't remember which one's bigger. It's probably treatment because of how I simulate the other ones. But 0.006, this big jumbled mess here of a scatter plot, there's no way you'd be able to tell that's a negative correlation using your eyes, but I got a p-value of 0.003. So when sample sizes get large, very, very, very small effects are statistically significant. I wouldn't say they're significant in the everyday sense, but they're significant insofar as, even though this scatter plot here looks like just random junk, the size of that negative correlation, small as it may be, is larger than we would expect to see by pure chance alone if in fact the correlation, the population level correlation, were exactly zero. And so therefore it's statistically significant. My favorite example, this is a paper on eBay data called How Many Cents on the Dollar, Women and Men in Product Markets. Women had a slightly higher percentage of transactions for which positive feedback had been given in the year preceding the current transaction, 99.60% for women, 99.58% for men, and then the magic word, p less than 0.05. Yeah, there you go. 2/100ths of a percentage point. Well, the sample size was in like the hundreds of thousands. So you have a big enough sample size, anything. I don't think this should be taken seriously, but there it is, with its small p-value. So the big lesson there is don't confuse how interesting or large an effect is with how statistically significant it is. They're not the same thing. And on the other side of things, just because you didn't get statistical significance doesn't mean you have evidence that there is no effect. It just means that the evidence you got, the data doesn't disagree with the null by enough to declare statistical significance. You can get non-significant, if the null hypothesis is true, you're likely to get non-significance. You have a 95% chance of getting non-significance if the null is true, but you can get non-significance pretty easily if the null is false and the power of the test is low. So power is a really important concept in statistics. It's the probability of rejecting a false null hypothesis. So if the null, in other words, if the effect really exists, what's the probability that you will get statistical significance? You can think of it as like a detection probability. If the effect really exists, what's the probability that I'm going to detect it with this test? And sometimes there's decent evidence that there's a lot of like low power research being done. Sometimes it's hard to get high power. If the data are really noisy, or the true effect is fairly small, and you aren't able to control for things carefully, then you may have low power, and so if you have low power, so in this case, like if you fail to reject the null, then the question is, well, why did I fail to reject the null? Is it because the null is true, or is it because I had low power? And you don't get to know that. You can make assumptions about what the true effect size might be and do power calculations, but you don't really get to know the answer to that. Here's my visual argument here. So I just made up some confidence intervals. If you're not familiar with these, a confidence interval, you can think of it as roughly like a range of plausible values for the unknown thing. That's not rigorous, but it's good enough for us. And down here, these -2, -1, 0, 1, 2. Let's suppose those are this thing called the Cohen's d statistic, which is how far away two means are from each other in terms of number of standard deviations. It's a pretty popular effect size. We have these silly like arbitrary cutoffs, but the arbitrary cutoffs for d that most people go along with is like 0.2 is small and 0.5 is medium and 0.8 is large and like 1 is really big. So like if means are different from each other by a whole standard deviation, that's considered to be pretty big. And so down here where it says 1, think of those as large effect sizes, and then the values close to 0 would be small effect sizes. And so here are 3 pretend confidence intervals that maybe you could get from some actual data. I set them up in such a way that the p-value in all 3 cases is 0.51. So you can get one p-value can correspond to an infinite number of confidence intervals. You move the center of it and you change how wide it is, and you can just keep the p-value the same. So in this case A, I have a p-value of 0.51, so of course I fail to reject the null hypothesis. I do not have statistical significance in this case. And the trick when you have a confidence interval and you're testing against the null of 0 is like if 0 is in the confidence interval, then you don't reject that null. So 0 in this case is a plausible value for the difference, and so I don't reject the null of the population mean difference being 0. But in this case of A, like 0 is in there for sure. 0 is in that interval. So is -1 and 1. And did I fit 2 in there? I'm not quite sure. But this giant interval is consistent with either no effect or a massive effect. So if you get this, you just haven't learned anything except that this is not informative. So these are, I would call these uninformative results up here. C down here, that's got 0 in it too, and it's really narrow. So for C, I would interpret that interval as either the true difference is 0 or it's small. So this is consistent only with small differences or maybe 0 difference. My claim here is you really, really, really should not be interpreting A and C the same way. Yet they both produce the same p-value, 0.51. They both lead to the same decision, fail to reject the null hypothesis. So this is my visual case for don't assume the null is true just because you didn't reject it. Next issue, publication bias. So results that are statistically significant are just more likely to get published than results that are not significant. Is this a good idea? I don't think so. I mean, I think, as I say in this bottom bullet point here, if a question is worth asking, isn't the answer worth knowing? In my opinion, who's at fault for this? I don't know. There's a lot of journals, a lot of reviewers who don't want to publish your stuff if you don't have significance. There's probably a lot of authors who don't want to share their stuff with the world if they don't have significance. But whatever the mechanism is, statistically significant results are much more likely to be shared than non-significant results. And I'm claiming here that this creates a biased impression of the overall state of research. If you're doing a literature review, only the successes, quote unquote, successes are going to show up and the failures are absent. What if there were just as many failures as there were successes, but you only see the successes? Ooh, I don't like the idea of that. There's ways of diagnosing this, so that there's pretty overwhelming evidence for publication bias in many fields. Just a couple tricks people use. This thing down here on the left is called a funnel plot. And what they do here is they've plotted effect size as measured in the data with what we call standard error. Standard error is roughly like how wrong you think your estimate might be, maybe the standard amount of error in an estimate. And at the top here, the vertical axis is small standard error, and the bottom is a large standard error. And then on the horizontal axis, there's some measure of effect size. In this case, it was a log relative risk for studies trying to assess how good rodent models are for studies looking at colon cancer prevention in humans. this picture shouldn't look like this. If there were no publication bias, this picture shouldn't look like this. And the reason is, when we go at the top, so when standard error is small, our error in our estimates is pretty small. So I'm going to tend to sort of believe the estimates up here at the top more than I'm going to believe the ones at the bottom. The bottom, they just have more statistical error, more possibility for getting much different estimates based on random chance. But we should be getting different estimates or variability in estimates in both directions. Like this line right here, let's suppose that this line were the truth. Down here at the bottom of the graph, I should see just as many points over here on the right side of this funnel as I see on the left side of the funnel. Well, the ones on the left side of the funnel are the statistically significant results in favor of the research hypothesis. And the ones that would be there on the right are the ones that are not. And so this looks like evidence that some stuff is missing, that should be there. We're not seeing the right pattern. This is a paper that randomly selected, I think, 1,000 psychology papers, just doing a search through the PsycInfo database, and they pulled p-values from all of them, and they converted them to z-statistics just for sort of convenience of the plot. Some of you may know that 1.96 is the magic number for z that corresponds to 0.05 as the magic number for p, and here's this line right here, 1.96, and what we see here is the mode of this distribution are results that are just barely statistically significant. And that is, and when we cross the other side of this threshold here, we see a huge drop in the number of results being published. The problem is the threshold is arbitrary. It's 0.05 because Fisher gave us that, and you said, cool, okay. If it had been 0.03 or 0.07, would this just we shouldn't see this difference. Those bars should be pretty much the same height. The fact that they're so different is evidence for publication bias. There's a bunch of other methods too. And so publication bias, I said it can give you a false impression of the overall state of research on a topic. It can also inflate the published effect sizes that we see. So publication bias says that significant results have a higher chance of getting published than non-significant results. In some fields it's overwhelming. In some fields you hardly ever see a non-significant result published. And then there's this issue of power I talked about before. Power is like the probability you'll reject the null if the null is false. If power is low, then there's a really good chance that you'll get non-significance. You know, if power is 40%, then there's a 60% chance you'll get non-significance, and only a 40% chance you'll get significance. And the kinds of results that will be significant are the larger ones. So if there's a lot of statistical noise and a lot of just variability due to chance in this study, whether it's observational or experimental, what that means is depending on your sample, you might get different results. You take one sample, you calculate some results. You take another sample, you get some other results, and the big ones will be significant and the smaller ones will be non-significant. Now, if we throw away all the non-significant results and we only retain the large ones, that means like the mean of the results that we retain is going to be a lot larger than whatever the true population mean for this effect is. So if it's a difference in means for like a drug versus a control, or if it's the strength of a correlation between two observational variables, whatever it is, we're going to tend to see, if we only look at what gets published, we're going to tend to see overestimates. And the phenomenon is worse, the bias is worse the lower the power is, because the lower the power is, the more stuff we're throwing away. And so I've got a visual example here. This is a simulation. And this is just for another t-test kind of situation where we're looking for a difference in mean, so imagine it was control versus treatment. And let's suppose that the population mean effect size is d equals 0.5. So at the population level, in truth, the difference between control and treatment is half a standard deviation. But there's a ton of variability. Power is low. So this may be because the sample size is small, or maybe because what we're measuring is just hard to measure and there's lots and lots of noise. At any rate, I've simulated this so that power is 0.3. So there's only a 30% chance that you're going to get significance. There's a 70% chance that you're going to get non-significance. Well, I've color-coded the significant results red here. So the red results on this histogram are the significant ones, the gray results are the non-significant ones. If we throw away the non-significant ones, meaning if we have like complete publication bias, then, and we do a literature review, we would think that the mean effect size is the mean of the stuff in red, which in this simulation is 0.89, about 0.9. The actual mean is 0.5. So this is effect size bias. And we see this a lot, like when people do replication studies. Almost always, the replication effects tend to be smaller than the original published effects. Well, that's exactly what we would expect if we have a combination of not even low power, even just moderate power, and publication bias. The next question is like, is this stuff even necessary in the first place? Like, is a declaration of statistical significance useful for us? Most of the time when we're measuring things, I shouldn't say most of the time, depending on your field, a lot of you are collecting data that are continuous in nature. There are a lot of fields where data are categorical as well. But then we do proportions. You can kind of think of proportions as almost continuous depending on how big the sample size is. We have these statistical summaries that tend to be continuous, and then we just draw a line somewhere, and we say everything on this side of the line gets this word, and everything on this side of the line gets that word. And I just sort of wonder, like, is this even necessary? Is there really a decision to be made? I think most of the time there isn't. Sometimes there is. So, if you've got money and you're trying to figure out, you've got a limited amount of money and you're saying, do we move this research project forward? You have to make a yes/no decision. Do I spend this big pile of money on this thing? That's a real decision. But very often we're just reporting our results. We've done the research. We're reporting our results to everybody else. Is there an actual decision that's being made? I don't know. It feels to me like no, usually. It feels to me like when I read a paper, like you could just give me other summary statistics. You could summarize your results without any need for a declaration of significant or not significant. I very often just don't really see the point. Except, of course, that it's like requested from you. You were told to do it in statistics class. So I'm arguing that it's kind of pointless, but it's worse than just pointless to me. I think it can be harmful, and insofar as it leads to these false impressions, like if you get statistical significance, that means the thing is real, and if you get non-significance, it means the thing is not real. Those are bad ways to interpret these kinds of results, but that's how it makes sense that that's how we would think about them, because that's sort of how it feels. You're making a declaration one way or another. So to me, I prefer just reporting effect size estimates and putting confidence bounds around them. So making confidence intervals is my preferred alternative. I should say that there isn't always an interpretable confidence interval that goes along with a statistical test. So there are some statistical tests where there's a p-value, but there really isn't a confidence interval that also makes sense. But most of the time there is. If you're looking at means or differences in means or slopes or correlations or odds ratios or relative risk, or all of these things, these are interpretable statistics that you can think of as effect sizes that you can put an interval around. And to me that just conveys more information. I might say more about that later. Another issue, another source of confusion here when we go around labeling things significant and not significant. This is a fun paper here. The difference between significant and not significant is not itself significant. Okay, what's going on here? I see very often in papers where there are like, you try the test for this group and you try the test for this group, and you say, oh, well, for this group the results were significant, and for this group they weren't, and so therefore there's a meaningful difference between these groups. That's not necessarily the case. You didn't just test them against each other. Testing two different groups against zero and making a significance or non-significance conclusion is not the same thing as testing the groups against each other. But very often we treat it as though it is, and probably the simplest way to understand this is, imagine you have these two groups and you're doing the same test for both, and in one case you get a p-value of 0.04, and in the other case you get a p-value of 0.06. You have to be mad to say that those results are in disagreement with each other. They're practically identical. But the magic line is right between them, and so one is called significant and one is called not. But if you actually compare them directly to each other, that would certainly not be a statistically significant difference. Here are some visual examples from this paper. So this was estimated effects of electromagnetic fields on calcium efflux from chick brains. And this plot on the left is a plot that looks like what was in the original paper, and well, the shaded bars are the statistically significant results, and the non-shaded bars are the non-significant results. But then here are some corresponding just estimates with standard error bars around them. The plot on the right is not what we're used to seeing. These bars are one standard error as opposed to the usual two. So a confidence interval is like two standard errors on either side. But the point here, so look at like around 400 hertz over there. You see that there's a couple significant ones, and then they're surrounded by non-significant ones, right? But like, there's just, ooh. So should we really be saying that like that one disagrees with that one? I mean, God, they're almost the same. They're almost the same, but like one passed the magic threshold and one didn't. That doesn't mean that they're disagreeing with each other. By the way, if you want to make these kinds of comparisons, you look. We test for an interaction. So this is the appropriate way to do this. Is what we call testing for an interaction. Okay, and then the claim here is we got a lot of sort of bad incentives, I think, and that have led to, at least in part, are partly responsible for this so-called replication crisis. Some people think that word is a little overblown, so I'm not necessarily endorsing the term, but the phrase replication crisis has been used in many fields. It was very prominent in psychology and in cancer biology. There's been some in neuroscience and economics and marketing research. And so what this refers to is replication teams going in and trying to reproduce results that were already out there in the literature. So some study was conducted, results were reported. Well, I mean, part of the scientific method is we're supposed to be able to do things over and over and get roughly the same results. And so these replication teams go in and they try to reproduce results, and they quote unquote fail to replicate. Now, personally, I think there's also an issue with the definition of non-replication. I think that this arbitrary nature of declaring things significant or not, this problem also shows up in the somewhat arbitrariness of calling something replicated or not. You know, like, do we say it's a successful replication because the p-value is less than 0.05? That's what I was just criticizing a second ago. So there are some arguments over exactly how to define a replication. We never expect two results to be exactly the same. But even then, we do see some dramatic stuff, like replication projects in psychology showing, if we just forget about significance for a second, average effect sizes in the replication studies being half of the average effect sizes in the original papers. That's pretty, I won't say significant, pretty large. So why is this happening? Well, there are these practices that go by lots of different names. Some people call them QPRs for questionable research practices. You may have heard of p-hacking, which sounds really nasty, like just chopping the data up until a small p-value falls out somehow. Researcher degrees of freedom, I like that, just like having flexibility of what kind of analysis to do, and then choosing the one that gives you the smallest p-value. Phishing, data dredging, salami slicing, da-da-da-da. So the whole idea here is you're making data-dependent analysis decisions. You're deciding how to analyze your data based on your data, and you're going with the analysis that gives you the smallest p-value. No, bad. We're not supposed to do that. The reason we're not supposed to do that is that kind of practice leads to false positives at a much higher rate than we're supposed to have. In principle, we're supposed to have this 5% false positive rate. If in fact the null is true, you're only supposed to have a 5% chance of rejecting it. That's why we care about a small p-value. Like, you ask yourself, why was anybody ever convinced by a small p-value in the first place? The answer was supposed to be hard to get by chance. Well, if you engage in practices that make it easy to get by chance, then who cares if it's small, right? here's that definition again of the p-value. The probability that, if the null hypothesis were true, a new sample of data from the same population would produce a test statistic at least as large as the one calculated. Well, implicit in this definition is that if you had a different set of data, you would have performed the same analysis. Otherwise, what's this even referring to? It's saying what's the probability that a different sample of data would have given you a test statistically as big? Well, if a different set of data would have resulted in a different analysis entirely, then this is, I mean, it almost feels like a category error. Like it's like, this is a probability of something uninteresting if we're going to be doing different analyses with different sets of data. So if you feel like you've done the analysis in such a way that like maybe had the data been different, you would have chosen something else, that p-value is not, it's not a probability of anything all that interesting. Now there's ways of fixing this. There's like multiple comparisons corrections, multiple testing corrections you can use, but the multiple testing correction has to capture all the potential flexibility in analysis that existed. Here's a nice little visualization I made of it. So that's the t statistic for a two-sample t-test when you're comparing means to each other. And sometimes I've seen plots like this where they show like the horizontal axis is doing the bad thing, and the vertical axis is type 1 error rate. There's a little line that goes up, where it's like the more you do the bad thing, the higher the error rate. But I like this one. This is more dramatic to me. So this is, the blue distribution is our good old friend, the theoretical t distribution. It looks basically like a normal distribution. And then this distribution in red is the distribution of that statistic that I simulated when I engaged in a practice that I'm not supposed to engage in. In this case, it's collecting data, checking the p-value. If the p-value is less than 0.05, you stop. If the p-value is bigger than 0.05, you collect some more data and try again. If you do that, then the distribution that you sampled the statistic from is not, in fact, that blue distribution that it's supposed to be. It's this wacky little red distribution with bumps. Those bumps are just past, by the way, the thresholds for statistical significance, of course. So when you engage in flexibility like this, what you're doing is you're taking results that would have been in the middle and you're pushing them out towards the significance regions, but just far enough to get 0.05, less than 0.05, then you stop. That's why it creates those weird little bumps there. Okay, so that's a big laundry list of complaints about statistical significance itself. Notice I didn't complain all that much about the p-value in particular, so I want to make this distinction, because these things very often get sort of thrown in the same pile. P-values are the most popular tool for declaring statistical significance, but we can declare significance with anything. You can use a confidence interval if you want to. If 0 is outside the interval, the results are significant. Or you can just make something up. A lot of people are getting into like Bayes factors these days. And we see people say if the Bayes factor is more than 10 or less than 0.1, then something magical happened. You can draw an arbitrary threshold and make a declaration of significance using any statistic you want. It just so happens that we tend to use p-values, but I want to be clear that criticism of significance is not the same thing as criticism of p-values. Most papers try to make this clear. Here's this quote from this special issue of the American Statistician. We are not recommending that the calculation and use of continuous p-values be discontinued. Where p-values are used, they should be reported as continuous quantities, e.g. p equals 0.08. They should also be described in language stating what the value means in a scientific context. So, yes, the reason they say this is there's this sort of goofy practice of like, if the p-value is bigger than 0.05, people just write not significant and not even tell you what it was. Or if it's between 0.05 and 0.01, they just call it less than 0.05. Like you don't get to know, tell us the number. But otherwise, you can still use p-values and not use significance if you want to. It might be tough to get the 0.05 thing out of people's heads. It's like the don't pick a pink elephant thing, but you could do it. That being said, I do have some criticisms that are specific to p-values themselves and not necessarily statistical significance. This is a quote from John Tukey, who the ever-quotable statistician John Tukey. This is from a 1991 paper on multiple comparisons. Statisticians classically asked the wrong question and were willing to answer with a lie, one that was often a downright lie. They asked, are the effects of A and B different? And they were willing to answer no. All that we know about the world teaches us that the effects of A and B are always different in some decimal place for any A and B, thus asking, are the effects different, is foolish. This is pretty strongly worded. I can think of counterexamples to this. There are some hypotheses one can come up with that I think really are just like utterly null, like no, that thing doesn't actually exist. But for most of the things we're testing, I mean, think about, again, I'll use the drug example. Like you read a paper and they've tested one drug against another drug or a drug against control, and the null hypothesis is that the mean effects are equal in these two groups. Kind of like Mickey Mouse research team you got going on that's produced a drug that does literally nothing. Or two drugs that do exactly the same thing. You know, I'm not in that field. That seems rare. Most of the time when I look at p-values, they're testing against a null that I don't even think could be true in the first place. The population correlation being exactly 0. If you're doing observational research, the population correlation is not 0. Everything's correlated with everything, at least to some small level. And so if the null couldn't even be true in the first place, then exactly what is to be gained by knocking it down? I can say, in other words, if the null is a straw man, who cares if we reject it? There are some examples that we encourage some people to do this in stats class, by the way. So I'm guilty of a lot of things I'm complaining about up here. I'm trying to be better because I teach statistics. So you may have heard of some of these things: Shapiro-Wilks test for normality, Kolmogorov. I always have to stop for a second before I say Kolmogorov-Smirnov test for equality of distributions, Levine's test for equality of variances. I know SPSS spits this one out automatically when you do ANOVA. And the reason is, so I'll just do Levine's test here. There's this assumption that the population variances are the same. You're comparing means across groups. Maybe the means are different, but we assume the variances are the same. I think it's insane. Like if the means are different, why aren't the variances the same? In fact, I have a hard time imagining any actual treatment you could impose that would change the mean but wouldn't change the variance. That seems very strange. Anyway, it's an assumption. It turns out you can violate it. Maybe not too severely. It's nice if you have a balanced design where your sample size is the same. It's nice if your sample sizes are bigger, but you can get away with some amount of violation of this assumption without having horrible results. And sort of ironically, the bigger your sample size is, the more kind of okay it is to violate this assumption. But the bigger your sample size is, the more likely you will get a significant violation of the assumption. So the null hypothesis is the population variances are the same. You get a p-value less than 0.05, you reject it, and people go, oh no, I have a statistically significant violation of my assumptions. As I said before, statistically significant doesn't mean large. So a significant violation of your assumptions is not necessarily a consequential violation of your assumptions. And if you fail to reject that null hypothesis, it doesn't mean you're in the clear. So this practice of doing tests for nulls that aren't going to be true. Shapiro-Wilks test for the null hypothesis is our data came from a normal distribution. They didn't. There you go. The question should be how, is it close? Is it really non-normal? Do I have huge extreme outliers? Could this variable take on outliers? If it's like an index variable, the answer is no. But imagine, could it take on outliers? Then you might want to be worried. But testing to see if the data themselves are significantly non-normal, I don't think really contributes a whole lot. There's this little quote from a statistician, George Box: all models are wrong, some are useful. Okay, other complaint about p-values, they're very, very commonly misinterpreted. Some of you may have experienced this. You took a stats class, you're told this weird thing, and you're trying to make it make sense in your head, and every time you make it make sense in your head, your teacher tells you it's wrong. That's because it's weird. And so this is a quote from Jacob Cohen of Cohen's D. What's wrong with null hypothesis significance testing? Well, among other things, it does not tell us what we want to know, and we so much want to know what we want to know that out of desperation, we nevertheless believe that it does. What we want to know is, given these data, what's the probability that the null is true? But as most of us know, what it tells us is, given that the null is true, what is the probability of these or more extreme data? So, the very common misinterpretation of p-value is something along the lines of the probability that I'm wrong. I get a p-value of 0.02. Cool, 98% chance I'm right. It's not what it means. But that's sort of how it feels. And I think the false interpretations are easier to understand than the real ones. So to maybe kind of demonstrate this. This is very, very non-rigorous here, but roughly you can think of the p-value as the probability of your data given that the null is true. This is that little line means given right there. So probability of data conditional on or given that the null is true, and this is not the same thing as the probability that the null is true given your data, and nor need these be similar to each other at all. So sometimes I've had this conversation before where I say, well, the p-value is not the probability of the null being true. And so I say, well, I know that's not technically right, but close enough, right? No, the probability of the null being true could be very, very different from the p-value. Let's imagine some extreme scenarios here. Let's say we have some research program in which no true null is ever tested against. Probability that the null is true is 0, just because you're not testing against true nulls. Or let's say you have some weird research program where you've managed to only test against true nulls. The probability of the null being true is 1. Some of you, for those of you who are familiar with the frequentist interpretation of probability, you're probably getting like a little bothered right now. You're like, oh my god, he's saying the things that you're not supposed to say. So just to be really clear here, under the classic, what we call frequentist framework of probability, the data are random. The truth is not. So hypotheses refer to claims about the world which are going to be either true or false. There's nothing random about that. Then we collect the data, and we model the data as being random. And we're only allowed to make probability statements about the data. And we're not allowed to make probability statements about hypotheses in the classical framework. So in the classical framework, in which p-values are used, probability of the null being true is not even a meaningful statement. It's either true or it's not. Now, we can go into a different world. So that's there's another interpretation of probability called the Bayesian interpretation of probability, and that interpretation treats probability more as like something that's up here in your head, like it's a way of describing a state of information or a state of knowledge or a state of belief. And in that case, you can have probabilities of hypotheses. But, I'm not gonna. That's a whole other can of worms that I won't go into. Okay, I mentioned before that this special issue of the American Statistician made this "don't say significant" claim, that was not an official ASA statement. This was an official ASA statement. This came out in 2016. It's a statement on p-values, and this was controversial too. It's not as exciting to read as the recent one because they got 20 statisticians to agree on it. And so if you get 20 people to agree on something, it's probably not going to be the most fun thing to read. Right? There's not going to be any flowery language in it. But here's what they said. P-values can indicate how incompatible data are with a specified statistical model, basically how much the data disagree with the null. But they don't measure the probability of the hypothesis being true. They don't measure the probability that the data were produced by chance. So I hear this a lot. The p-value is the probability that my data occurred due to chance. No. It's the probability that if the null hypothesis were true, data like yours or more extreme would occur due to chance. They sound like the same thing, but they're not. We shouldn't be making scientific conclusions and policy decisions based only on whether a p-value passes a threshold. Proper inference requires full reporting and transparency. In other words, say everything you did, not just the stuff that worked, quote unquote. P-values don't measure effect sizes. I've already gone over that. So this is an official statement. Again, it's not that exciting to read, but there is some fun stuff. There was a set of supplemental statements that came out with this. So the people who contributed got to write their own supplemental statements, and those are fun because they're all like, "This is what I really should have said." And you get to see where all the argument was. So even something as bland as that was kind of controversial as well. Okay, so that's my big overview of what I think are problems. On to the section about recommendations, about what we could do differently. So the special issue of the American Statistician, moving to a world beyond p less than 0.05, well, they better tell us how we're supposed to do it. So They summarize this big piece of advice using this acronym ATOM, and they say accept uncertainty, be thoughtful, be open, be modest. That all sounds lovely. Let's see what they meant. Accept uncertainty. Statistical methods don't rid your data of uncertainty. So we don't have it's not the uncertainty laundry machine where you have all this ugly, messy data and you don't know what the truth is, and you toss it in the statistics machine and you put the button, then the truth pops out all nice and dry on the other end. That's not what we're doing. We can quantify uncertainty. We're good at that. We're not very good at washing it away. They say use confidence intervals when you can, just because they're more interpretable. Like the units of the confidence interval are the units of the thing that you're actually interested in, not this weird probability that nobody seems to fully understand. Ask yourself, does adding a p-value add any additional useful information beyond what you've already reported? And then the usual stuff statisticians say. It's easy for us to say this, isn't it? Seek better measures, more sensitive designs, larger samples. Yeah, I get to sit in my office and tell people to collect larger samples. Okay, be thoughtful. Ask, what are the practical implications of the estimate? How precise is the estimate? So this is what I love standard errors. The standard error, I think, is an underappreciated statistic. It tells you roughly how wrong you would expect your estimate to be. And that's hopefully is interesting. Be open. So there are these open science practices like pre-registration, I'll talk more about in a second, transparency with what you did, data sharing, code sharing. There's kind of a movement towards this of sharing data and code that will run when a paper is published. Give sufficient information so other people can not only reproduce your results, but maybe try to execute meaningful alternative analyses. Be modest. Remember that these are all models. Models are simplified versions of reality. So when you run linear regression, the model says, here's where data come from. You have some values for X, your predictor, and then you go up to this straight line that exists at the population level, and you go to the line, and then you pluck a value at random from a normal distribution with some variance, and that's where your data came from. It's not where data come from. It's a model of where data came from. So we're using models here, and we want to remember that models can have limitations, and that models are usually simplifications. There's no such thing as a true statistical model. The true model is reality, and I can't fit that, so we simplify. Be modest about the role of statistical inference and scientific inference. There's more to scientific inference than statistical inference. There's more to uncertainty than statistical uncertainty. I've been talking about, we talk so much confidence intervals, standard errors, margins of error. These are all based on what we call statistical uncertainty, the uncertainty that comes from the fact that if you take a new set of data, you'll get different results. But there's more, there's like forms of bias, right? What exactly is it that you're measuring? Are you measuring the thing that you want to measure? Your confidence interval is not gonna fix any problems there. So there's much more to inference, broadly speaking, than just the statistical part. Encouraging others to reproduce your work. I got a few slides on more specific recommendations. Some came from this special issue. So this was called Valid P-Values Behave Exactly as They Should. So this says, present P-values for more than one possibility when testing a targeted parameter. For example, if you discuss the P-value from a test of a null hypothesis, also discuss alongside this null P-value another P-value for a plausible alternative parameter possibility. So in other words, you don't have to make the null be 0. You could make the null be some other effect. And this kind of goes back to that whole failing to reject the null is not the same thing as showing proof of the null. Like, maybe you fail to reject a null of 0, but maybe you also would have failed to reject a null of 0.2 or 0.5 or whatever the value is. So you've got actually that's what a confidence interval is. A confidence interval is a range of values that you would fail to reject if you tested against them. So maybe it could be interesting to see what a p-value would be for some other value that isn't null. That was kind of a new one on me, but it sounded cool. False positive risk. This paper says compute, in addition to providing a p-value or a confidence interval, compute this thing called a false positive risk, which is the probability that the claim of a real effect on the basis of the p-value is in fact false. So it's that thing that we're saying people want. It's like the probability of the null being true given significant results. I have a little aside that I put in here. This requires you to put a prior probability on the null. So we're moving over into Bayesian land when we do this. If you're comfortable with that. There's also, I like the suggestion here, specify the prior probability of there being a real effect that would be necessary in order to get a false positive risk of some value like 5%. And the idea here is like, if you would have had to have a prior probability, if the prior on the null would have to be pretty small in the first place in order to get this 0.05 that you wanted, then maybe what you did didn't add much more information. You can read the paper, it's a little bit weird, but interesting. This is a similar idea. Again, it requires priors, but put a lower bound on the probability of the null being true. Take the p-value and then apply this formula that lets you sort of flip it around and make it be the probability of the null itself, and report a lower bound on that. Again, this requires priors, so maybe we don't want to go there. Okay. Pre-registration and registered reports. I'm a big fan of this model. A lot of journals are doing it. More journals every year get on board with this. If you Google registered reports, you'll see a list of participating journals. And what a registered report is you go through the peer review process before you've collected the data. So you say, here is my question of interest. Here is my proposed methodology. Here's how I'm going to collect the data. Here's how I'm going to analyze it. Here's what I'm looking for. Here's why you should care about the result. And if that's accepted, if that goes through review and it's accepted, then the journal agrees to publish your results no matter how they turn out, as long as you do what you said you were going to do. And so this goes along the model of like, if the question is worth asking, isn't the answer worth knowing? And so they say yes, and so you can do it this way. There's a lot more work up front before you collect the data, and less work after you collect the data here. I like this a lot. There's some preliminary studies on the use of registered reports are showing significance rates around 50%. Of course, it's going to depend on the field, right? But significance rates of around 50% of studies that are done using this model, half the time they get significance, as opposed to like 99% of the time getting significance when we don't use this model. So the Association for Psychological Science has been out in front on a lot of this stuff, and they did this cool thing. They offered badges for doing good stuff, little gold stars that you can put on your paper if you get it published. There's the Open Data Badge, the Open Materials Badge, and the Pre-Registration Badge. They're just little icons that say, you did this thing that we like. And it's amazing how much effect it can have. In the couple years before they started doing this, like the open data thing, I think data sharing rates in APS journal papers were around 3%. And then the year after, they were like 40%, and they're even higher now. So just rewarding people, you know, because most of the time there's no reward. Like it's just more work for you and to share your data. But sharing data, like if you have that, if I see the Open Data Badge, I know I can go check, and just the fact that anybody can go check maybe will make me trust the results a little bit more, possibly. Maybe you'll be more careful. If you're sharing your data, you know that like somebody else could look at what you did. If you're reporting results and you claim that you have support for the null hypothesis, remember that non-significance is not the same thing as evidence for the null, as said earlier. But if you want to find evidence for the null, there's ways of doing it. We can't give you evidence for the point null of exactly 0, but what we can do is make like a sort of pseudo null that's just a small range around 0. So there's this method called equivalence testing where you specify the smallest effect size of interest. You say, hey, if the effect of this drug is less than 1/5 of a standard deviation, I'm not even interested in pursuing. So you set up d equals 0.2 as your minimum effect size of interest, and then you sort of flip the traditional null. The null becomes that the true effect size is greater than this minimum effect size of interest. If you reject the null, then that's evidence. You interpret that as evidence that the true effect size is less than this minimum effect size of interest. So it's kind of a cool way of flipping around the traditional null alternative. Of course, I don't think, to me, just make a confidence interval. Like I don't want to hear the statement about significance. Like you can just make the confidence interval. And like if the confidence interval is narrow around 0, then you have evidence for either a null effect or a very small effect. If the confidence interval is wide, then it's just who knows? Some advice for reviewers. There's this thing called the Peer Reviewers Openness Initiative that calls on reviewers to require some of this stuff as a condition for reviewing. So I don't know, this is probably more popular in some fields than others. Some people may have a stomach for this sort of thing, and others might not. You're being kind of demanding, but say, yeah, give me code so I can see what you did. I would say just in general, like, remember significance is not the arbiter of truth. And also be aware that it's really unlikely that you're gonna get lots and lots of significant results over and over and over and over again unless power is very high. So power of 80% is this number that gets targeted a lot. It comes from the same place as 5%. Like somebody made it up and we use that because we've been told to. But power of 80% is this like desired thing. Like if you're writing a grant, like you want to do a power analysis and show that you have power of around 80%. Well, power of 80% means 80% chance of rejecting the null, 20% chance of failing to reject the null. So 4 out of 5 times you run this kind of test, you should get significance. I read multi-study papers a lot, where it's experiment 1, experiment 2, experiment 3, experiment 4. And they keep getting p-values just less than 0.05. That shouldn't happen. Like if power is high, you should be getting p-values less than like 0.001. And if power is low, or even moderate, you should be getting p-values above 0.05. But you see these studies, and like p-values between 0.01 and 0.05 happening way, way, way more often than they should. Again, there's evidence that there's some sort of selection at play. As an example, a bunch of journals have statistical reporting guidelines. These are worth looking over if you're interested. This is just an example from the New England Journal of Medicine. There are way too many to list, but here are a few. Methods section of all manuscripts should contain a brief description of sample size and power considerations for the study, like how did you decide on your sample size in the first place. Methods section of all manuscripts should show a description of how missing data have been handled. Significance tests should be accompanied by confidence intervals for estimated effect sizes, measures of association, In general, p-values larger than 0.01 should be reported to 2 decimal places. Let's report between 0.01 and 0.001 to 3. So you see these. You can look at other journals' reporting guidelines to see what they're recommending. If you're interested in this whole controversy on significance, there were some high-profile papers that came out. This was called Redefine Significance. There were like 80 or so co-authors on this and some fairly big names on it. And they said, it's too easy to get p less than 0.05 just by luck or by screwing around with your data. And so let's make the new threshold be p less than 0.005. And then you go, no, please, oh God, no. It's a suggestion. Incidentally, so I had a friend say like, oh man, in my lab, if we had to do that, we'd never get anything done. And it never published. Like, well, if you have 80% power for p less than 0.05, you've got roughly 50% power for p less than 0.01. So if you're doing well-powered studies, well-powered at 0.05, about half the time, you should be getting p less than 0.01. Throw that out there. Okay, our response here, justify your alpha. So this team said, how about instead of redefining significance, we have people state why they're using the alpha they're using. Like not all fields are the same. Like there's a balance between false positives and false negatives. If you have a lower alpha, you have a stricter threshold for declaring significance. Yeah, you'll have a lower false positive rate, but you'll have a higher false negative rate. You'll declare more things non-significant even when the effect is real. So there's a direct trade-off between false positive and false negative. So let's have authors just justify why they're using the number they're using. I've run this by a few people and they're like, I don't know how I would come up with that. Like this seems like, it just seems like everybody would say, well, I'm just using 0.05 because that's what we're supposed to use, right? And so there's been this other response here, abandon significance. This is the one I agree with. It just says, like, just get rid of the whole calling things significant. Practice entirely. So these are my personal opinions here. I tend to prefer estimation methods, like confidence intervals, as just standard practice. And try to estimate things that are interpretable. Like does the slope mean something to you? Let's talk about what the slope actually means. Does the D statistic mean something to you? Let's talk about what that means, then give the estimate and put an interval around it. I think it's very straightforward, and it just makes more intuitive sense to me than a p-value. and certainly not a claim about significance. I think claims about significance are usually uninteresting, especially if I don't think the null could be true. There are cases where the null could be true. We use these as demonstrations in class. Maybe you've heard of the lady tasting tea, the story about the lady was Dr. Muriel Bristol. She was a scientist. And she was at this party, apparently, and I can't remember if she wanted the milk in first or the tea in first, but the idea is like she rejected a cup of tea because they'd been poured in the wrong order, and people were like, what? Huh? No, there's no way you can tell. She's like, I can totally tell. And then so Fisher was at this party and did a little experiment to try to tell if she could, to try to see if she could really tell. Well, that's a case. That's a fun example, and what we do is we give students that example, and we walk away and we pretend it's always that straightforward. That's an example where the null is actually highly plausible, right? Like, I could totally believe that someone can't tell the difference. I don't think I can tell the difference. So you're dealing with a very, very plausible null. And I tend to be more interested in p-values when I think the null could even be true in the first place. But if it's like the treatment and the control are identical, I say, well, I just don't believe that. And so in those cases, I'm not really interested in p-values or statements about significance. I think plotting is underrated. So many times you read these papers full of summary statistics. They're written like the worst prose in the world, right? Just sentences and sentences and sentences with summary statistics. Like, just show me. I would much rather see a plot of your data than a correlation coefficient, or maybe even give both. But like, it's amazing how many times you'll read a paper and all the stuff sort of describing the data. And it's like you could convey so much more if you just showed us the data. So I think that's nice. And if you're using a model, if you're using a regression model, like, does it make predictions? What kinds of values does it predict? Maybe plug in some plausible values or some common values into this model and say, like, for people in this group, we predict this, and for people in this group, we predict this. And if you're this age, we predict this, and if you're this age, we predict this. And just give me, like, and even, hey, plot them, even better, plot them. Like, say, like, what kinds of predictions does that model make? As opposed to just, like, is the slope, significant? Okay, that's sort of my rant here. If you're interested in talking about this more, I've given this talk to a few groups, and some people said, hey, I like this stuff, so we're putting together a list of interested people. You had to register for this. I'll at least, when I make a video of this, I'll send it out, and you can share it if you want to. If you're looking for statistical consulting, I think we have two of our consultants in here right now. So Julia and Zach they work in the statistical consulting lab. They're in our department. And consulting, at least initial consulting, is free for faculty and staff and graduate students here. So go to the Stat Lab website and get help. And I guess I'll leave it for questions if anybody has any questions. Anybody angry? Anybody like?
I think for me, it's more about like, who is your audience, really, and ultimately, like, whatever it is that you're producing, who's the intended audience for that research, and a lot of times, how we structure the data, how we analyze the data is dependent on who that audience is. So if I'm doing something I know is going to go to this group, I might play with things a little bit differently than if I'm producing a report on the same data for this other group that maybe has a different threshold for
Absolutely.
Statistical language.
Oh,
and so
yeah.
I think for me, in terms of thinking about how we discuss that, I think you have to take pieces from all of it. Not only talking about, well, here's the statistical significance, but really here's more of like what we might interpret as like a practical significance. And while this may not be mathematically different, we can sort of see an overall pattern, for example, that shows that there may be something here and sort of lead us in a particular direction.
I couldn't agree more. It's very well said. Yeah, writing for your audience. When I collaborate as a statistician, when I collaborate with somebody, I ask, like, what background do most people who are going to be reading this have? Like, what do I need to explain? Is going here a little bit too weird? So I totally agree. The thing I said about pictures, like, pictures, everyone understands pictures, right? So I like to err on the stuff that's more understandable to more people. And I definitely agree with you on this idea of, like, practical significance versus technical statistical significance. Like, don't just tell me the statistical result, like, tell me why I should care.
yeah, the .05, I mean, didn't that really originate, and again, it's easy to do plant agronomy experiments where that stuff came from. But Fisher and others, I think that you're not going to mislead yourself too often if you use .05.
Right, yeah.
I mean, it's not entirely arbitrary. It came from looking at things, and so, you know, if you use .15 or whatever, you're gonna screw up.
Yeah, it's
An unacceptable amount of time. If you use .05, you're probably not gonna lose your job, you know, or you're not gonna mislead the farmers very often.
Sure, so, yeah.
And I think the same thing comes even with your confidence intervals. Like, it's pretty damn arbitrary to use 95%.
Yeah, why not 99, why not 93?
And along those lines, I like to use 1.5 standard deviations.
Yeah.
From a practical standpoint, for most people in most situations,
Yeah.
and 1.5 is easy. I think 2 is too strict in a way, and often you see plus or minus 1, that doesn't mean a hell of a lot.
Yeah, plus or minus 1 is about 68%, plus or
Yeah.
minus 2 is 95%.
Yeah,
Yeah.
and 1.5 is pretty close to 90, so you're 5% on each side. You know, that's what I come along with it. Lots of experience in not misleading people and myself.
Yeah, so I want to be clear, when I say the word arbitrary, like it's not I used it in sort of a critical way, but we can't avoid it. So I say arbitrary just to be like, there's nothing special about .05. We have to pick a number, but certainly the concept of not wanting to fool yourself too often is very important. That's the original justification, the argument for this. So one of the common counter arguments to most of what I set up here is, look, if you get rid of this and it's just everything goes, like the whole point of the p-value is so that we don't get fooled by randomness, so that we don't go thinking we've discovered something real when actually it's just a bunch of noise. And then picking .05 says, well, if it's all just a bunch of noise, you'll only conclude you found something real 5% of the time. And of course, other people come and say, well, what about the other error rate? What about the false negative rate? You know, the lower you push that, the more often you will say that you didn't find anything, there really is something there. So there's that. It's a straight up balance. And 5% was chosen. And for whatever reason, 80% was chosen for power. And Neyman and Pearson, I think, argued that like a 4-to-1 ratio for type 1 and type 2 errors seems...
Well, the problem is, I mean, you want it to be 99% or 95%, but you can't afford to do those experiments.
Of course.
So you compromise.
And some people would say you're being wasteful if you're power.
But there's a big difference between 0.8 and 0.5.
Certainly.
And so I'm happy with 0.8, 0.9 versus a lot of experiments that are less than 0.5.
Well, so I didn't really get into it, but there are certainly ways of trying to estimate average power across research. Yeah, in some fields it's better than others, but yeah, there are certainly some fields where we have pretty strong evidence that average power is fairly low. Yeah, it's an issue, and I totally take what you're saying as far as the confidence intervals. I'm up here saying I love confidence intervals, but a response to that is that a confidence interval is just an inverted hypothesis test. All it is the range of values that you would not reject at 0.05 if it's a 95% interval. So those endpoints are arbitrary too. So I'm saying I like confidence intervals, but certainly I'm not going to say like, oh, because it's on this side of the left endpoint, I'm going to treat it differently than if we're just on this side of the left endpoint. Like, don't take those endpoints too terribly seriously. Other questions or comments?
So an interesting sort of corollary to your publication bias is the more prestigious the journal, the less repeatable the studies are.
I've heard that, yes.
And that's partly, and you could see that just by not anybody cheating, but just by chance. You get an interesting result by chance, and so it becomes more or a big effect.
Chance and novelty. So I think a lot of the bigger journals want to publish novel results, and novel results are just more likely to be flukes. You know, the boring stuff tends to work better. You know, anything else?
So one other wisecrack.
Sure. Yeah.
You talked about understanding your model and what you're studying, And I use the extreme of the lead in the head experiment. We want to, we're going to kill, pick its species, bad animals. And we're still going to shoot them in the head, see if they die. No, you get the bullet in the head, and the first one dies. And he said, well, maybe that was by chance. You do another. You don't have to do that 3 or 4 times with that model. Well, that's an extreme, but there's a whole spectrum of that sort of stuff. And so understanding your...
The Bayesian in me would say you'd want to put a pretty high prior on the animal.
Yes.
Yeah. maybe 50% is not the best starting point for that model.
Yeah. Right.
Yeah. Cool. Well, we have the room for a while, so I'll hang out if anybody wants to talk to me. There's a bunch of there's some literature. There's like cards there, I think, from the Stat Lab. So if you're interested in more information about the Stat Lab, our consultants are over there. There's stuff on the table. Thanks for coming by. Appreciate your time.